Okay, so I'm live, folks, so I won't be able to answer questions during the talk, but I'm very happy to answer questions afterwards and throughout the day. Thanks very much to the organizers for putting together this fabulous workshop and for inviting me to participate. So imagine a car traveling 60 miles per hour. In the back seat, a baby sound asleep, and in the front, that baby's parents also asleep. As someone who's about to have her first baby and who has spent countless hours even just looking up the safety of car seats, such a scene initially makes the hairs on the back of my neck stand up, probably yours too. But one day soon it won't. Instead, we'll rest just as easy as these parents, knowing that artificial intelligence has given us self-driving cars and the safest roads in human history. AI promises to take humans and our flawed intelligence out of machines. Why then do I think that we should put babies and their early intelligence into machines? My research in developmental cognitive science convinces me that babies have a lot to teach machines and will help them learn better. Not only will babies help us build better machines, but machines will help us build better babies. How? Well, AI promises to help us better probe the origins and development of human thought. With what we learn, we may then design educational programs that, in a sense, help us build better babies. Developmental scientists suggest that infants' intelligence is founded on at least 3 cognitive capacities. The first is a series of domain-specific knowledge systems that allow infants to recognize and interact with particular facets of human life. So, for example, infants have knowledge about physical objects. They expect objects to move cohesively, independently of other objects, only when acted upon and with shape and size constancy. So for example, when young infants are shown, say, a rod that's occluded by this rectangle here as depicted in this schematic, and that rod is moving in a continuous and cohesive fashion, when the rectangle is removed, infants expect that there is one continuous rod presented behind or present behind the occluder, as opposed to 2 different rod parts. Infants also have knowledge about agents who have goals, act efficiently towards their goals, and unlike objects, can generate their own movement. So for example, if infants watch, say, that little ball there on the left-hand side schematic, jump over a barrier to achieve its goal, getting to the big ball, and then that barrier is removed, the infants expect that little ball to move directly or efficiently to that ball, to the big ball, instead of taking the trajectory that it had taken when there had been an occluder in the way or an obstacle in the way. Again, infants expect these agents to move efficiently towards their goals. Similarly, infants expect agents to have consistent preferences in their goals. So for example, if an infant watches an agent reach towards a ball, a preferred object, then infants will expect that this goal is consistent. Even if the ball changes its location, the infants will expect that agent to reach consistently towards the ball in its new location. So infants also have knowledge about places, so whose layout, geometry, but not landmarks or surface properties, we and even other animals use automatically to get from one place to another and regain our heading after being disoriented. So this particular schematic is taken from a really classical paper that was done with rats. So here what we're looking at is an overhead view of a rectangular environment where, say, a little treat was hidden for the rat at the bottom right-hand corner, that black dot. And the rat was disoriented in this chamber, and the question was, how would the rat regain its bearings to find the target location? And it just so happens that the rat used the geometry of the layout, so the fact that there was a long wall on one side and then a short wall on the other side that defined the geometry of the treat to regain its heading. But it went equally to that black dot in the diagonally opposite corner of the chamber that had the same geometric relations as the target location, but had different surface properties or landmarks. So the idea here is that in our intuitive conception of places, we pay attention to layout geometry and ignore these landmarks or surface properties. And again, this is an example with rats, but it's just the same in young children. So in addition to these domain-specific knowledge systems about objects, agents, and places, infants have a set of learning mechanisms that enables them to build efficiently and effectively on their knowledge. And finally, of course, there's infants' readiness for language. So when we consider that infants' knowledge is built on these very early emerging cognitive capacities, we realize that our most fundamental knowledge thus really isn't learned. It's already been learned for us through evolution. And I saw this topic come up in the chat. Love to discuss it more later with folks who are in attendance. Okay, so one of the challenges, nevertheless, of building AI is deciding what knowledge to start with. So some believe that AI is most elegant or powerful when it emerges from nothing, written on a blank slate, coded only with ideal learning mechanisms, like, for example, Bayes' rule, which exists in every human mind, but also in the abstract realm of mathematics, so it can be programmed into a computer. With such mathematical tools, the best AI should be able to learn anything and everything, and simply. But I argue we should give AI both mathematical and cognitive tools, leading to AI that looks like, and indeed has common sense like, human intelligence. So I believe there are at least two areas where it's clear that we should want AI to look like human intelligence, allowing AI to better understand us and us to better understand AI. AI that understands us could better capture the complex behavior of human societies, from business transactions to international relations. Likewise, AI that we can understand could better explain such complex behavior to us. The goal of science has traditionally been to explain the world rather than just predict its behavior. AI can do all the complicated computation at once, but without a common vocabulary, grounded in common intelligence, we may not be able to understand its results. And so, if our goal is to make AI inspired by human intelligence, where do we start? First, I think there needs to be a way to put tests of human intelligence in direct dialogue with tests of AI. Can AI perform as successfully as infants on tests of the domain-specific and abstract knowledge at the foundation of infants' learning and reasoning? So doing this requires a scientist to cross disciplinary boundaries and collaborate to come up with a suite of tests or benchmarks of intelligence that can literally be used both in the experimental protocols of developmental cognitive science with infants and also in the strictly computational evaluations of machines. So while some work in cognitive development has certainly been inspired by computational research and findings, and likewise, some of which we've heard today, some work in computational cognitive science has been inspired by findings from cognitive development, no work to my knowledge has yet made the kind of direct connection that I'm calling for. And there are likely many reasons why this is the case. I think one main reason maybe is that such tests of intelligence for infants and AI have to balance and resolve the limits of testing both infants and AI, and this is not an easy task. So for infants, the literature evaluating intelligence is rich, but also necessarily fragmented and incremental. Infant studies are often conducted with small, select populations and highly controlled lab settings, and studies rarely collect data from the same infants over time. These limits make it hard to identify what are the most essential and robust properties of human intelligence and what knowledge builds on what developmentally. This is a problem for making tests for AI because, well, it's hard to determine what content and what processes should be the target of those tests for AI. So also for infants, experimental paradigms using, for example, looking time or preferential reaching are contingent on what infants can actually do. And often the measures are indirect measures of infants' knowledge. These problems, or these paradigms, excuse me, have thus often constrained our understanding of what infants know, and still may not fully exploit, given the paradigms we have, still may not fully exploit what we can learn from infants. This is a problem for AI because those paradigms are going to constrain the tests that we're going to be able to give AI as well. And third, our inferences about how abstract infant knowledge are often based on only a few key experimental contrasts, varying only one or two key variables, and often presented to different groups of infants. For example, conclusions about the specificity of infant social intelligence often rely on a contrast between a condition with positive findings using, say, face stimuli, and null findings using upside down faces or shapes. So conclusions are not based on experiments that present many kinds of non-social stimuli and vary exhaustively on any would-be orthogonal stimuli properties. So this is a bit of a problem for AI because the way to test abstraction often in tests of artificial intelligence are by procedurally generating many, many kinds of tests that do exhaustively vary any would-be orthogonal properties that are not at the crux of the abstract content or process that's being tested. So in terms of the AI side, there are also some limits that I think come into play. So for AI, training sets can never really capture the richness of human life, or infant life in particular, which is what prepares infants for many lab tests of intelligence. So again, this is something that's come up already today in the Q&A. Happy to talk about it more. While it's true that infants can often succeed in the lab with one or few examples, it's nearly impossible to identify what quote-unquote training set or prior experience made them ready to appreciate those examples, or what specific experience were most relevant to their success. And Those experiences are exactly what we need to identify and include in AI training to put AI on an equal playing field with infants for these tests. AI can also cheat in many ways, often in ways that we humans do not, would not, or perhaps cannot. So while tests of AI must protect against such cheating, tests of infant intelligence have never really had to worry about, for example, how one pixel in a stimuli display could give away the answer. And finally, to succeed on these tests, AI not only needs to have models of human intelligence, but also it needs to have the appropriately coded perceptual systems to even get access to the tests in the same way. Infants have ready-made perceptual systems that make the input of the test stimuli easy, but processing the stimuli as input to the AI is an engineering challenge in and of itself. Okay, so despite all of these challenges, our little team at NYU, a true collaboration between my lab and the lab of my colleague, Brendan Lake, and I should also give a shout out to the other members of our DARPA team, including Lisa Oakes, Colleen McCrank, David Moore, and Victoria Romero at CACI International. We're interested in taking several domains of early knowledge and creating tests of intelligence that can be used with both infants and AI. So I'll just give you a brief overview of some of the tests we're creating to evaluate knowledge of agents, okay? So in particular, we're focusing on our understanding of agents that includes their having goals, they're acting efficiently, and they're taking instrumental actions to meet a goal, but only when necessary. So I'm just gonna show you a couple examples of what we've been working on. So these are works in progress. They include 8 habituation trials, followed by 1 test pair, and are based on the violation of expectation looking time paradigm that's typically used with infants that, again, we've already heard about today. So happy to have had that introduction already. The videos are paired, the test videos are paired such that one video has a test trial with an expected outcome and one has a test trial with an unexpected outcome. And the idea is that infants would look longer at an unexpected outcome relative to the expected outcome, and AI models would produce some metric for each outcome indicative of the expectancy. So what I'm going to show you here is just a comic strip version of our first example evaluation, testing agents having goals. And the habituation phase can be schematized just like this. So there's a little salmon colored square agent, and he is going to move to his preferred object, that little blue pentagon here. It's outlined in purple in the videos, which we'll see in a second. There is no such outline. This is for your ease of viewing. And as you can see, the blue pentagon is in a sort of consistent location in this 2D grid world throughout the habituation. So this kind of 2D grid world being used as kind of an evaluation environment is somewhat typical of tests of artificial intelligence. So we're using it here as potentially a test in and of itself, but also they'll be the foundation off of which the engineers we're collaborating with at CACI will form more realistic 3D worlds capturing some of the same principles. So we have these habituation trials, which again, we'll watch the video in a second, and then the test trials look like this, where now the location of the 2 objects, the sort of general location of the 2 objects is switched, and in the unexpected case, the agent goes to a similar location that he had visited before, but now the non-preferred object is there, so he's visiting that non-preferred object. And in the expected case, we have the agent visiting going to the preferred object, the object during habituation that he showed a consistent preference for. So I'm just presenting these habituation and test sort of videos. I'm not presenting any examples of the training sets that will accompany these test videos. Again, I think there are really important decisions to be made about these training sets, and I'd be happy to talk more about what we're thinking about the training sets later on or in the Q&A. Okay, so let's watch these videos, and I'll just let you guys pay attention. So remember, we're going to watch the 8 habituation trials first, and then the 1 test trial. Okay, So here we have our freeze frame on the test trial. And as you can see in the unexpected case, the agent goes to the object that had not previously been preferred, but was in a similar location to where the object, that preferred object had been. And in the expected case, the agent goes to the preferred object now in a new location. So again, that is one example. Here's another example of an evaluation we are thinking about that's probing infants and AI's understanding of agent efficiency. So what you'll see here, again, I'm not going to show the comic strip version, just show the video. The object location is similar in all the habituation trials, and hence the motion is similar too. At test, the object appears in one of the locations it had been during habituation. In the unexpected case, the path taken is the same as one of the habituation trials. The expected path, in contrast, is entirely novel. So let's take a look. Okay, and this is our test pair here. Now, again, this is one way that we could kind of test this idea. You could see that the distance between that little home base and the object was matched across the unexpected and expected outcomes. The timing was a little bit different. Again, this is one variation of many that we could generate that would sort of probe this idea that agents are acting efficiently. Here's a last example I'll provide. Evaluating whether infants and AI would be able to detect or be able to sort of judge the idea that agents take instrumental actions towards their goal, but only when necessary. So I'll narrate this one a little bit as it's going. We have our agent picking up this special little key. The key releases a green wall so that the agent can go access its preferred object. Okay, and here, again, in our test pair, now we have it being sort of unexpected here that this agent whose ultimate goal is to get to the pink pentagon, it's unexpected that he would go to the key when the key no longer has an instrumental purpose in achieving the agent's goal. So again, many different variations are possible. These are the ones that we're thinking about right now. So before I mentioned limits to our testing, when that testing has to be appropriate to both infants and AI. Nevertheless, as the past few slides have shown, I don't think the effort is impossible, and surely it isn't in vain. And that's because in addition to there being limits to our testing ability, these very limits afford an expansion to our understanding of both infants and AI. So for AI, there are obvious gains in computational efficiency. In particular, AI can harness the evolutionary heritage that's made humans the most efficient learners known to us humans. AI would also increase its range of applicability and ultimate mastery of common sense, as common sense tasks that currently it crucially fails at. It currently fails at. So for infants, Successes in AI would allow for new opportunities to test the robustness and generalizability of our developmental theories. In particular, we can present AI with exactly the kinds and quantities of variability in test stimuli that are completely impractical when testing infants one-on-one in the lab. If AI fails in one of these cases, we can take that test into the lab and see if infants fail too. By this exhaustive testing of common sense AI, we can therefore make new predictions about human intelligence without exhausting our babies. For infants, finally, we may learn about new kinds of things we should be looking to measure. For example, AI may be able to provide much more insight into the content and processes behind a violation of expectation. This might suggest to us ways to probe infants in content and process in ways that underlie their violation detection, perhaps even inspiring us to innovate paradigms and measures. So just in conclusion, let's have developmental cognitive science and AI toddle together, driving each other forward. Thanks very much. In particular to the organizers, my lab and collaborators, funding sources, and the Machine Common Sense Project at DARPA, and the generous families who participate in our studies. Happy to answer any questions.